Welcome back. In this video, we're going to talk about nonlinear optimization. So, what is optimization? Um, what does it mean in mathematical terms? So, a typical optimization problem relates to finding the minimum or maximum of a function, right? Optimization refers to both minimization problems and maximization problems. What does that mean? For example, let's say we have a function f of x of one parameter, right? X is the independent variable, or in this case, the parameter that we're seeking, and we want to find the value of x such that f of x attains its minimum value, or in some cases, we would like to find the maximum value, right? So this is why we refer to minimization or maximization problems. Both of them are optimization problems. And we can remember some rules from basic calculus when we have a function of one independent variable, one parameter here in this case, x. There are a few tests that we can use to decide whether a particular point in the x-axis is a minimum or a maximum. The first requirement for both minimum and maximum, as you can see from this figure, is that the first derivative of the function f of x must be 0 at that point. If it's not 0, for example, here in this point in the middle, then that means that there is a direction where I can go that will increase the value of the function, and therefore that point cannot be a maximum, a global or local maximum. We'll talk about that in a second. Right, and so here we have a minimum of this function, and here's a maximum of the function. And that's different from the roots of the functions that we just talked about a few other times. So how do we decide whether a point is a minimum or a maximum? Well, we look at the second derivative of the function at that point. If the second derivative of that function, which again, the second derivative implies curvature, as we all know from calculus, if the second derivative is negative, that means that parabola is pointing down, and this is going to be a maximum at this point. If the second derivative is positive, then this parabola is pointing up at this point, and in this case the extremum is a minimum. So in mathematical terms, we refer to these problems as optimization problems, and there are two kinds again, the minimization and maximization. When it's a minimization problem, we write it like this mathematically. This means find x, or minimize over the parameter x of this function f of x. Conversely, the maximization problem can be written as maximize over the parameter x this function. Right? So whenever you see this notation in textbooks and papers and websites and so on, that's what it means. It's an abbreviation. Why is it useful to be able to solve optimization problems? We already saw some problems that were written as optimization problems way back when, for example, when we talked about fitting a model to some given data in such a way that the model passes closest to the data, right? So find the model parameters so that that model builds a function, and that function passes as close as possible to the given data. And that, so we defined a measurement of how close a function passes through some data, and that was the sum of squared errors between the model and the data, and we found the model parameters that found the minimum value of the sum of squared errors, right? That was a minimization problem. There are many other types of applications where, in fact, almost all engineering problems can be somewhat written as an optimization problem. For example, if we have to find the shortest distance between 2 points, there are many options to get from point A to point B, right? There may be many roads, but there might be one road that has the distance that has shortest distance between these 2 points, right? Of course, if we were talking about air travel, for example, the shortest distance would be the straight line between these 2 points, right? Discounting the curvature of the Earth, for example. But in this case, when you're driving by car, you cannot drive over land, you have to go roads, so there are a few options, and you choose the shortest distance. right? You might decide to do this if you are, for example, a company like Coca-Cola delivering bottles from one city to the other, right? You want the drivers to spend the least time on the road, the least fuel, and so on, right? In other, there are many applications for optimization problems. Here, this other example we have here, you might want to optimize some chemical process. Uh, so, for example, you can have two axes. In the x-axis here, you have the pH of some particular enzyme, and here you may have the activity of that, and there may be some pH value where you get the most activity for that particular enzyme. So that's also an optimization problem, just to give you a sense of how important knowing about optimization and how to solve it in computers it actually is. So as we already saw, in one dimension, when we're seeking for one parameter, right? In this case, we're talking about the parameter being x, right? If we have a quadratic function, right, ax squared plus bx plus c, then it's relatively easy to find the minimum or maximum of that particular function, because, let's say in this case a here is positive, there will be only one value where this function attains the minimum. That's the whole nature of a quadratic function. How do we find that one? All we have to do is differentiate with respect to x and solve for where this first derivative equals to 0, right? That's more or less the test we had written here, right? Find where the first derivative is equal to 0. In one dimension, that's true, right? Then we can set this becomes a linear equation on the unknown parameter. There's just one unknown parameter and one equation, so we can easily solve this. We also saw that when we have a multivariate quadratic equation, where now x here is not a single number but a vector, there is the equivalent form of a quadratic equation in this vector form, where a here is a symmetric matrix. And if now we have multiple parameters, so we have many partial derivatives of f with respect to each element of x. So how we write this set of partial derivatives, we call this the gradient, right? But if we set this gradient of this quadratic multidimensional equation to 0, we end up with a linear systems of equations to solve, where we can use the matrix inverse definition to write the solution for x. This is all fine and dandy for quadratic functions. Here's the bad news. The bad news is that a lot of engineering problems are not that simple, right? The optimization the functions that you're trying to optimize over are not quadratics. There are certain special situations where the function turns out to be a quadratic. For example, I mentioned again that example where we try to find the model's parameter for a linear model, and we try to measure the squared error between the linear model, and some data. That's known as a linear least squares problem, and that linear least squares problem for a linear model again turns out to be a quadratic function, which we can differentiate and write the solution in closed form, as we just did. But many engineering problems are not that simple, meaning the function that you're trying to optimize over is not a quadratic function, either in 1D or multi-dimension, but it may be a cubic, a fourth order, more general, some sinusoidal type function, or something else that you may not even know. You may not even be able to categorize it, right? There are many functions like that we define that we really don't know much about what they are, but we would still like to find at least a local minimum or local maximum for this function. So in this case, we use what's called as a numeric optimization method. It's an iterative method, and the whole idea is to start with an initial guess. We call this guess x naught here, and again x is in bold font here, so we should understand that this x is a vector really. And then we start with this one, and then we just update it. We find a new guess. We call this x1, and we check, is the value of the function at x1 smaller than the value of the function at x0? So in this case, we're looking at a minimization problem, and either way, either a maximization or minimization problem are the same. You can use minimization algorithms for maximizing a function. All you have to do is take the negative of that function, right? So you flip the function, and you can use a minimization algorithm to maximize a function. Conversely, you can use a maximization algorithm to minimize a function. Again, you just take the negative of that function. So in a broad sense, these algorithms address the same problem. So step 3, in this case, going back to what we're talking about, we check whether the new guess is better than the old guess, and if so, we repeat. We keep improving. Right? So that's the general strategy for pretty much any numerical iterative optimization method. So here's the good news, is that optimization in some ways is like root finding. And we already covered several algorithms for root finding, so you already know how to do this. Why is it the same as root finding? Because as we just defined, right, the minimum or maximum of a function can be defined as the location or the x-coordinate where the first derivative of that function is 0. Well, if I have to find, so we can call the first derivative function df dx, call it some function g. Doesn't matter what you call it, but it's just another function. And we have to find where g is 0, or in other words, where the derivative of this function is 0. This, it's just semantics. We already solved this problem. All this means we have to find the roots of g. Right? So we've saw 2 general strategies for finding roots, or finding the zeros. In this case, in this optimization context, finding the zeros of the first derivative in one dimension. Those were the bracketing methods. A couple examples we covered are the bisection and the golden section method, for example, and open methods like the Newton's method, right, the secant method, and so on. And again, there are pros and cons to these methods. Bracketing methods tend to be more reliable as long as you have a correct initial bracket, but they tend to be slower than open methods. Open methods can be unreliable, meaning they can diverge, right? But when they converge, they tend to converge much faster than bracketing methods.